And now we get to the heart of the matter, self-adjoint operators. So self-adjoint operators are operators that have a high degree of symmetry that allows us to do a lot of hands-on analysis with them. So the definition is pretty straightforward. We just say that an operator on V, and so notice here, we're assuming that the codomain is V. This is an operator that we're talking about now. Previously we were looking at maps from V to W, but now we're just looking at maps from V to V. So this is said to be self-adjoint if it's equal to its own adjoint. And so functionally what this means is that if we've got it on one side of the inner product, we can just move it to the other side of the inner product, and we don't even have to pay with a star. We just schlep it back and forth, just as handy as you please. Okay, so real numbers are the complex numbers that are fixed under the involution of conjugation. They're equal to their own conjugate, right? Self-adjoint operators have an analogous role. Analogous. Oops, and then I ran out of space. Roll. Sorry about that. So, in the space of operators. So, self-adjoint operators, or maybe let's just say, to keep the grammar parallel, self-adjoints are the operators in LV that are fixed by the involution of adjoint, right? They form a subspace. So scalar multiples of self-adjoint operators, at least by real scalars, are also self-adjoint, and so are sums of self-adjoint operators. But they do not form a subalgebra. Maybe, yeah. But they do not form a subalgebra. And that's because ST star is T star S star, and you don't necessarily know that those operators commute with each other, right? Okay, so now we have our first result about self-adjoints, and that is that the eigenvalues of a self-adjoint operator are real. Okay, and so this is kind of making this analogy precise, right? So real number, you take the conjugate, you get the same thing. For self-adjoints, if you take the conjugate of their eigenvalues, you get the same thing. So remember what I said earlier, the eigenvalues are sort of like the number version of an operator, the numerical fingerprint of an operator. By the way, there is a whole long storied tradition in mathematics of building analogies between number systems and corresponding operators. So this role of the real numbers within the complexes and how it's reflected in this in the role between the self-adjoint operators and the full collection of operators. There's similar things that are done for the well, the integers is a subset of the rationals, and the rationals is a subset of the reals. And there's various versions of all of this stuff for operators as well. And this comes up all over the place in number theory and all kinds of junk. Anyway, blah, blah, blah. Okay, back to the theorem at hand. Yeah. Okay, before we go on to the theorem at hand, go look up the Wikipedia page for the Langlands program. This is a field of mathematics that deals with basically fleshing out the analogy between primes within the integers, and then comparing that to certain types of groups and the divisibility of like groups and rings and vector spaces and stuff. You can do the same things sort of on different levels with respect to factorizability. Okay. Enough of that. Okay. So, let's see. The eigenvalues of a self-adjoint operator. Okay, we're going to need an eigenvalue. So let's suppose that TV is lambda v with v non-zero, so that we have an eigenvalue-eigenvector pair. Okay. Then, and I love this proof because it's slick, simple, straightforward, and it just shows the beauty of inner products and the importance of self-adjoints all in one. So let's see. So we're going to take lambda times the inner product of v with itself. And so if we use linearity in the first slot, then we have lambda v times v. But by our definition, this was tv times v. Right, TV is lambda v. And then by self-adjointness, yeah, so let me see. So this, I use that one, this one right here. And then by the fact that t star is equal to t, so we're assuming that this sucker is self-adjoint, then I can put the t on the other side. And then I can use the fact that we've got an eigenvalue-eigenvector pair again to translate this back into lambda. And so this is being used right here as well. And then when I pull a scalar out of the second slot, it comes with a conjugate. And from beginning to end, this tells me if I subtract lambda conjugate thingy from both sides, then I end up with lambda minus lambda conjugate inner product of v with v being equal to 0. Now this is a product of two things being equal to 0, so one of them has to be equal to 0, but since we assume that it's not v, since v is not the 0 vector, we know that the norm of the inner product of v with itself is non-zero. Whence? I love a good whence. We have that lambda is equal to lambda conjugate, which is equivalent to saying that it has to be a real number. And we're done.